Okay, seems to be working. All right, so yeah, glad to be back. Today we're going to be going over compiling simple IR code dealing with arithmetic operations into assembly code, specifically x86-64 AT&T syntax assembly. So that's a flavor of assembly we had discussed earlier that we're going to be reviewing in this course. I think the substitute should have covered some of that as well in the previous lectures. So before we start, I just want to remind everyone that the proc assignment is due tonight. So if you haven't started that yet, you probably want to start it now. It's, as some of your peers will probably tell you, a bit more challenging than previous assignments. Also, I want to point out, when you're completing the proc assignment, make sure to include the starter code in your git commit. So your code needs to be able to compile with the command make. So when you commit and push your code, make sure that whatever you pushed is sufficient to build with the make command. And you can check this by running the self-check. Yeah, right here. So you'll have to follow the steps listed in the Hello Project instructions and just adapt them to work with the proc project. But if you do this, you can verify that the code that you've pushed will actually compile when it is cloned or pulled in the grading server. So I recommend doing this just to make sure everything works. Remember, you don't want to push compiled binaries and executables and whatnot, but you do want to push any C code, any header files, anything that's not generated by any part of your build. You want to push that so that your code will actually compile correctly and we can actually grade it and give you credit. So any questions? Okay, so the into post project was also due yesterday. The exercise, I should say. Yesterday, or previous lecture, I suppose. So if you missed it, or if you weren't able to complete it for some reason, you have 2 lecture days to submit it for a regrade, resubmit it for a regrade. So that one should have been pretty easy. You were just manually copy and pasting code. The point of that was to get you familiar with ANTLR, perhaps the hard way of specifying ANTLR grammars. And today in this lecture, we're going to be going over more how to get started with the compiler project. So I think in the previous lecture, Ryan, he had begun introducing the compiler project to you. In this lecture, I'm going to show you some of the code and how to actually get started completing that project at the end after we go over the arithmetic operations. So any questions? Okay, so for now, I'll close this window and we'll start going over the homework. So this homework was maybe a bit tricky. You were asked to write a function in simple IR. So this is the intermediate representation we've been reviewing in class, to compute the nth element of the Fibonacci sequence. So does anyone remember or can tell me what the Fibonacci sequence is? Yeah?
So you can do like the sort of recursive way of define f0 is 0, f1 is 1, and fn for all other n as fn minus 1 plus fn minus 2.
Yeah, so Fibonacci sequence is a recursive sequence where the value at the Fibonacci value n is equal to the Fibonacci of n minus 1 plus Fibonacci of n minus 2. So we can translate this pretty intuitively into code. The challenge is doing this in simple IR. So in C code, this might be fairly easy to do. Let me actually open a window I already have open here. So if we were working in C here, we could probably do this pretty simply by just saying return, or if x is equal to, we'll start at 0, return 0, return fib of x minus 1 plus fib of x minus 2. Oops. And we'll have to add another case here for x of x equals 1. So this would be the C implementation of Fibonacci. Does this make sense? Are there any questions about how this works? This is a bit easier to read than the simple IR code, so I think I should show this first. Okay, so what are some challenges with translating this to simple IR that you may have noticed when you were completing the assignment? Yeah?
The restriction of not doing like true arithmetic in assignments.
Yeah, so there's no nested expressions in simple IR. Every expression, every assignment has only a single operation on the right-hand side at most, or a function call. And you can't nest expressions inside function arguments. What's another potential challenge with translating this to simple IR? Do we have structured programming with simple IR? Do we have if statements in the traditional sense like we do in C here, where there's braces? No, right? What do we have instead? What's the more lower level construct we have that enables us to branch? Go-to. We have go-tos and labels. So part of the challenge here as well is translating this structured code to unstructured or imperative simple IR code where we just have labels and conditional and unconditional branches. So I'll type this out here in a comment on the bottom so we can have both for easy reference. Maybe not actually. My editor is adding all those extra characters. Might be easier just to do it in a separate window. Fib.ir. Okay. Oops, I already have some code here. I'll delete this. All right, so we need at a minimum, we need to declare our function. So we use the function keyword to do that, and then end function at the end of the function. We need a local variable, we need our list of local variables, which has to be a superset of our parameters. So our parameters are, in other words, a subset of the local variables. We also need a return statement for our result. I'll just put this here at the bottom. And we'll have to add a new local variable for our result. So far we've just written some boilerplate code for the Fibonacci implementation. Let's move on to actually writing the actual code for computing the Fibonacci number. So what's the first thing that we should probably do? Yeah?
So we want to define our base cases. So
Mm-hmm.
What I did is if n less than 2, return n. Is that something you can do?
Okay, yeah, we could do that. So how can we, well, I guess the way we would do that is to assign, well, we could just do if go-to, right? So if x is less than 2, go-to, and then we can say, we have to add a new label here, so we'll say end. And maybe to make this simpler, what we can do is just say result is equal to x initially. That way we don't have to change this line of code at the bottom. So result is equal to x. If x is less than 2, i.e. x is 0, 1, or 0 or 1, then we just return that same x as the argument. Okay, any questions so far? All right, so we handled the base case. Now we have to handle the recursion. So we're going to have to translate this single return statement here into simple IR. So how can we do that? What do we need to do first? So remember, we can't store we can't have nested expressions in simple IR. So we need to store these intermediate results here, this call to fib, and even this expression within the argument of this call to fib as separate variables. So we'll need to create some separate variables for storing x minus 1, x minus 2, fib of x minus 1, and fib of x minus 2. We'll need to create separate variables for storing all of that. So we'll create some more up here. We'll say y and z. We'll set y equal to x minus 1. We can set z equal to x minus 2. And now let's create some more variables for storing the results of fib of x minus 1 and fib of x minus 2. So we can say f1 is equal to call fib y. I think that's the correct syntax, right, for simple IR. We use the call keyword when we're calling a function. F2 can be call fib z. And then what is the result equal to? Exactly, f1 plus f2. And I think that's it. I think that should work. So any questions about this recursive implementation of the Fibonacci sequence? Okay, so there are other ways to implement this. You didn't have to do the recursive approach. You could have taken an iterative approach. That would have been perhaps more complex, depending on how you do it. But recursion normally maps pretty intuitively onto the Fibonacci problem, even though it's by far not the optimal solution in terms of time efficiency. The iterative approach is often better, including the dynamic programming approach, which you might be familiar with if you're taking CS2. But for our purposes, it's pretty intuitive to take the recursive approach here. All right, so any questions about the homework before we continue to the main lecture for today? Okay, so I'll close this. Close this. Yeah, and the Fibonacci sequence up because I couldn't remember what the sequence started with. All right, and today we're going to talk about arithmetic. So this is a pretty, I think, gentle introduction to the compiler project and implementing the first set of features with it, which is integer arithmetic.
This is CodeGen 1.
Yeah, this will be useful for CodeGen 1 specifically, which I think opened up.
Yeah, it's open.
Yeah, it should be open. Today it's due on the 15th, so you have a lot of time, and many students actually find that these last few CodeGen projects are pretty quick to implement, but they're a little tricky conceptually. So especially this last one, CodeGen 3 is probably going to be the most challenging, but CodeGen 1 and 2 should be pretty quick to implement if you can grasp the concepts we review in class today. All right. Wrong slide. Here we go. Wrong page, I mean. So our goal for today is to turn the simple IR expressions of this form, x equals a plus b, arithmetic operations, into the corresponding assembly code. So what is this process called when we convert some source level language to a lower level language? Not interpreting, not interpretation, but the other one. Compilation, right? Compiling. So normally, often we'll say compilation is converting some source level language into machine code, but really you could argue that compilation is any high level language to a lower level language. So there's some challenges with doing this, that we have to handle the variable and integer constant operands, and we also have to handle the assignment that we have, because as you can see here, we always have to have an assignment for arithmetic operations in simple IR. So there's three things going on here: the operands and the assignment, and then also the operator itself, but that's not going to be a big deal, as we'll see later. Every simple IR expression has the following form. So an operation consists of some kind of name, followed by the terminal, the literal := sign. Then a first operand, which is either a name or a number. And then an operator, which is one of these terminals: plus, minus, asterisk, divide, or modulo. And then a second operand, which is again either a name or a number. So the big idea, and we're going to be using a sort of a template for solving these, translating these simple IR expressions, is to just treat the left-hand side as the name, and then we have our operands and operator, and we just translate sort of all these just using a template. We're not going to be able to follow the template exactly for division and modulo, and we'll see why later in this lecture, but for most of these operations, if we can translate the operands and the name, we can just use that same template for translating all different kinds of arithmetic operations. Yeah, so operands can be integers, they don't have to be variables, and we have all these different operators we need to support. So to get the value of variables, we're going to be using the symbol table. So I don't know, did Ryan or Sanan review what a symbol table is in the previous lectures? Can anyone tell me? So does anyone remember what the base pointer is or what a stack frame is? I think we might have mentioned that term before I left. Yeah?
Is it you have a set of variables in contiguous memory? Is it is the pointer to where that memory starts?
Yeah, that's one thing what the base pointer is for. So what is the stack frame, more broadly? What is the stack frame? Does anyone remember what a stack frame is? I think we had talked about this before. So a stack frame is the region of memory, so this would be RAM, where a function call resides. So all the function's local variables, its parameters, they're all going to be placed in a contiguous region of memory called a stack frame. And this is often not going to be physically mapped to the disk. This will be, or to the RAM, this will be virtualized. So what the symbol table stores is the offset from the base of that stack frame at which each local variable of the function call resides in memory. So for instance here, we're saying that the variable x is at offset -16 from the base pointer of the stack frame that has this, wherever this code is being executed, for whatever function call is executing this code here. So we're going to see some concrete examples of this later in this lecture. But just to review, the stack frame is the piece of memory, region of memory where a function call lives, and the base pointer points to the base of that stack frame, the base address of that stack frame, from which all local variables and parameters are relative to. Okay, make sure. Okay. So to support accessing operands, the left and right hand side of an operator, we're going to be using the symbol table to tell us what offset to access them from, and we're going to be treating the base pointer sort of as like an array in C almost for getting the offset of which those variables are. So for instance, if A, as we saw earlier, is at offset -24, then the way you'd write this in C is with the brackets after RBP, -24. But in assembly, what we're doing instead is -24 and then in parentheses %RBP. So you just kind of flip the syntax around. Does anyone know why the offset is negative?
Is it because the stack goes down and
Yes, exactly. The stack grows down. So that's something to remember that's very important. The stack grows downward. According to the ABI, the application binary interface that we're following for implementing this compiler, the stack grows downwards. So negative addresses go closer to the base address, the 0. The low address, I should say, 0. So if we wanted to write an instruction to actually load a value from a variable and store it into a register, so remember a register is a small, fast-to-access piece of hardware on the CPU core. We can run, basically this assembly instruction is what does it. We would specify we want to load the value A, which is at -24, offset from the base pointer, into the RAX register. So source is the left operand, destination is the right operand, just left to right. A goes into, oops, so we can read it as move the value in A into the RAX register. So this might be like the opposite from MIPS if you took computer organization here. I think MIPS might have had it in reverse. So, yeah, so any questions so far? Yeah.
Does RAX, like, do those RBP and RAX, do they have like, are those like standard names or are they specific to like the variables A and B that we're using in the example?
So RAX is a general purpose register that you're allowed to use for whatever purpose you want. If you're writing a compiler, for instance, we're going to be using RAX for a lot of these examples just because it's the first one that's available to us as a general purpose register. It's just a coincidence that in this case we're loading the variable named A into RAX. RBP is a standard name according to the ABI, the Application Binary Interface. RBP is always going to store the base pointer of the stack frame that we're currently in. So you can look up the system v ABI for more information. I think that we can find it here. OS Dev Wiki, yeah, it's in my notes. I'll load this up. This is in the course notes, this link. Yeah, this tells you some stuff about some of the registers that are available to you. Yeah, RAX, RDI, RSI, RDX, all these ones are scratch registers. They're for whatever purpose you want. So you can honestly implement, just reading these 1, 2, 3, 4 paragraphs, you could implement most of the compiler yourself if you read them very carefully. So I hope that answers your question.
Yeah.
So remember, different architectures, different systems might have a different ABI, and so what we're doing here in this class may not apply to them, but x86 is very prevalent in computing, so this will get you very far if you just learn this ABI at least. All right, so for supporting integer operands, integer literal operands and expressions, we can just use a $sign prefix with a number, and that actually tells in assembly code that indicates a literal number value. So if we wanted to move the value 1 into the RBX register, we could just use move and then $1 RBX. Now if we want to assign to a variable, so I think if we saw, let's go back to where we saw earlier here, to move out of a variable, we use the offset from the base pointer to get the value out of the variable. We can do the same thing to move a value into a variable, we just flip the order of these operands. So in this case, if we want to store the value in the RAX register into the place in memory where the variable b is, I think that's b. Yeah, b is at -32. So here we're going to, from RAX into -32, we're storing the value in RAX into the place in memory where the variable b is. You might notice that in the symbol table, all the offsets are of increments of -8. Does anyone know why that is?
The number of bytes you need for that data type?
Yes, so we're assuming all variables are 64 bits in size. So 8 bits in a byte, 8 bytes, 64 bits. That makes things a lot simpler for our implementation of the compiler. However, a real compiler, like a C compiler, will have variables of different sizes, including structs, which are totally up to whatever the programmer defines those structs to contain. Yeah.
Or in a modern system, because I know that there is a, like you always have the 32 versus 64-bit system. When we declare an int, how much are we actually benefiting from the reduced memory of an int compared to a long, or a floating point compared to a double?
So it really depends on your system, because an integer, and according to the C standard specification, if you've ever looked at it, doesn't actually tell you the exact size of an int. It actually just tells you what the minimum and I think maximum sizes of those variables are. It really tells you a range of what those variables can be, or what those types can be, I should say. So I think on most systems, a long is actually the same as an int. You have to use long to get a different size than an int. Yeah. That's also why more modern languages, like if you ever programmed in Rust before, they have types like I32, I16, U64, because they make it more obvious to the programmer what exact size you're dealing with, because often it's nice to know the exact number of bytes you have available to you. C even has this. If you're using, I think, the C99 specification, or ISO specification, you can actually use the standard int header, which gives you like U32 types, for instance, for specifying exact bit widths of whatever variables you're declaring. Yeah.
Just that one, or any C since then?
Anything post C99 and onwards, yeah. So let's, oops, a little bit too far. All right, so let's see how we actually perform arithmetic in assembly. So for addition, we just use the add instruction. So the add mnemonic. And what this will do is add the left-hand side to the right-hand side and store the result in the right-hand side. So RBX plus RAX is equal to RAX equals RAX plus RBX. So just remember, the right-hand side is the right operand, and it's also the destination. Or, I'm sorry, it's the left operand. The right-hand side is the left operand, and it's also the destination. So the order here of the operands isn't really important in this case because addition is commutative. You can swap the order of the operands around and you won't be harmed. If you did that, you would mess up the destination register. But in terms of the operand ordering, it doesn't matter because addition is commutative. Subtraction, on the other hand, is not commutative. So you got to take great care when emitting a subtraction instruction that you got it in the right order. So in this case, what would this code be equal to? If the right operand is going to be the right operand to the sub-mnemonic is going to be the left operand of the subtraction and then also the destination, what would this be equal to?
A minus B.
Yes. Which one is what is equal to the result though? A minus B. A. Oops. Yeah, it's not listed here, but A RAX equals RAX minus RBX is what should be shown.
So that's A equals A minus B.
Yes. Yes. Yeah. We'll see an example shortly of that. So in this case, if we have addition here, what is the result of this addition? So add RAX to RBX. What register has the result, and what is the result?
14 stored in RAX.
Close. But remember, the right-hand side is going to be the destination, always. So 14 stored in RBX. And then in the second example, what is the result and where is it stored?
Still 14 is stored in RAX.
Yeah, exactly. So we're adding 9 to 5, and we're storing the result in the right operand, RAX. So we got the same result, but just a different register is where it's being stored. Now for subtraction, this is a bit trickier. So we have 9 and 5, and we're performing subtraction here. Sub RAX, RBX. What should the result be in this case?
Stored in RBX.
So the destination is correct, but in this case the value would be -4 because we're taking the right-hand side here is going to be the left operand in the subtraction. So it will be RBX minus RAX, and that's all stored in RBX. So RBX equals RBX minus RAX. So 5 minus 9 is equal to -4. And then for the second set of instructions here, what should this result be then?
Positive for RAX.
Yes, exactly. So RAX is 9, 9 minus 5 is 4, and then 4 is stored in the right operand, RAX. So far so good, I hope. A little tricky at first to get the order correct, but once you've got it, it just works. That's the nice thing about compilers. For your project, once you get it working once, you're done. Now multiplication is pretty similar to addition. Can you guess what this means? Can anyone guess what this does? And where's the result stored? Yes, RAX. So this will multiply RAX by RBX and store the result in RAX. So again, multiplication is commutative, so pretty simple. All right, so now I think we should look at some examples, and I'm going to show some examples of a stack frame here, and the base pointer and the offsets and everything. We'll go through the whole set of instructions for this, the assembly instructions according to this, corresponding to this simple IR code step by step. So in this simple IR code, we have a function called main with local variables x, a, and b. A is assigned to 9 initially, b is assigned to 5. and then x is equal to the result of a plus b. Then we return x and then end the function. Here's our symbol table, the same one as we saw earlier. X is negative 16, that's the offset. A is at negative 24 offset, and then B is at offset negative 32. The big idea is that we're first going to load the values in A and B into general purpose registers, RAX and RBX. Then we're going to actually perform the arithmetic, adding the values of those two registers together, and then store the result back into the offset of memory where the variable x is. Let's look at some code here. So loading A and B, we're loading from offset negative 24 for A into RAX, loading from offset negative 32, that's where B is, into RBX. And we're performing the addition, so we're storing the result of the A register plus the B register. RAX, RBX are often called by just their middle letters. So the A register and the B register, add them to each other, stored in the A register. And then in the end, we store whatever is in the A register into the offset where x is. So any questions about this general overview? I'm going to go into the example shortly. Okay, so let's take a look at what's going on actually on a stack frame here. So I have this whole stack frame illustrated. I know it's maybe a lot to look at. Here's the expression, the simple IR code that we're going to be looking at, x equals a plus b. Here are the 4 assembly instructions that we're going to be executing one line at a time. Here's where the registers are stored, what values they have associated with them. So the base pointer points to the base of the stack frame. We're going to assume the stack frame starts at 120. X is going to be at offset negative 16, so at negative 16, that's where the variable x is. A is at offset negative 24, so at offset negative 24, A is there. At offset negative 32, the variable B is there. And we're going to assume that the loads A equals 9, B equals 5 have already happened. So A is equal to 9, B is equal to 5. We don't know what's in RAX, we don't know what's in RBX, we don't know what's in X, so I'm just left them as a hyphen for now to signify that we don't know and don't care what's already in them. Okay, any questions before I start going through these lines of assembly code one by one? Yeah.
Is there a reason why it's incremented by 8, the stack, the offset?
Yes, so this is because, I think we had said this earlier, the integers we're dealing with are all going to be 64 bits in size. And you know how many bits are in a byte? 8. So 8 times 8 is 64. Well, I guess I should say 64 divided by 8 is 8. So that's why we have 8-bit intervals that we're decrementing the stack by. And what?
No, I figured. I was just wondering if if numbers like 32 were just specific to the example. I just wanted to.
Oh yeah, no, we're always going to be dealing with increments of 8.
Okay.
And you might be wondering why we start at negative 16 for x. I won't go into the details, but it has to do with the ABI. There's going to be some special values that are going to be stored at these two spots. We'll go over that later in a future lecture on function calls and how those are set up and teared down. But for now, we're just going to be skipping these two slots. You don't have to worry about them. Just know that in general, the base pointer is going to start at, or the first offset is going to be negative 16. Okay, so I think we can start. So what I'm going to do is highlight this line of code here in red to show that it's the one we're currently executing. So negative 24, RBP into RAX. So we're going to go to negative 24 here. The stack goes downwards, so we're going to be referring to the variable that's at negative 24, right below it. So that's going to be A. A has the value 9, so we're going to move the value 9 into the RAX register. So we'll put that here. This black. Move on to this instruction now. So negative 32, RBP It's right here. We're going to grab this variable, b, which is 5. We're going to move 5 into rbx. So I'll put that right here. Now I'll move on to the next instruction, which is going to be the add instruction. So what should the result of this be? How is this going to change? What register is this going to change? What is it going to change it to?
RAX equals RAX plus RB.
Yes. So RAX is 9, RBX is 5. Add them together and you get 14. We're going to store the result in RAX. So RAX becomes 14. Now finally, we're going to move the value in RAX into offset negative 16. So we're going to move the value here into the offset negative 16. The stack grows down, so that means that we're going to be referring to this variable right here, x. So after this, x will become 14. That's it. So I'm going to be doing a lot of these examples throughout the rest of this course, especially when we get back to the function call lectures. I'll be using a lot of these stack-based examples. Yeah. So any questions on what we just did? Yeah.
For the add, will you always be passing 2 arguments and then overriding the second one? Because like in MIPS, you could have passed 3 and then you would have a new destination.
Yeah, these are all 2 operand instructions. And you can actually check this. There's a website that we refer to in the notes. This gentleman, Felix Cloutier, I guess is his name. They've listed all the assembly instruction specifications for x86-64 assembly. So you can see here, for each of these instructions, you can see that it actually tells you the different variants, the different modes, as they're called. So in each of these cases, there's only 1 comma, which means that every variation of this instruction only accepts 2 arguments, 2 operands. And the way to read these is that, for instance, right here, oops. This means you can specify REX as the first argument and then some immediate 32-bit value as the second argument. This mode, for instance, specifies that the first argument is a register or memory value that refers to a 32-bit value, and then an immediate 8-bit argument. So this is like all the different combinations of types and sizes, basically, for the different arguments you can have for this different instruction. And you can go to this website and just view all the different assembly instructions that we look at in the course. I recommend not using ones that we don't review in the class. Last semester, I had a spate of students who didn't bother reading the notes. They just used ChatGPT to tell them how to translate simple IR to assembly. And they all ended up using this leave instruction on the final exam, which is really strange. So please don't do that. Use what we've gone over in class for omitting your assembly code on exams and on the project. Yeah, so I hope that answers your question. All right, any other questions? Yeah.
Do we have to remember simple IR for the exam?
Yes, you should know simple IR. It's a pretty small language, so it should be easy to memorize how it works. Yeah, just write like 1 or 2 short programs in it, and you'll be good. Plus, you will learn it pretty well, I think, as you complete this project, because you're going to be basically writing a whole translation tool to translate simple IR to assembly. So they're going to touch every single part of this language. Yeah.
Also, a quick question on that third line, the add portion. So it's basically just adding the value at RBX and the value at RAX. Does it always overwrite the value in the second argument?
Yes, always. The second operand is always the destination operand.
Okay.
Mm-hmm. Yeah.
So the RBP is separate from like RBP used to like describe the stack.
Yes, it's the base pointer of the current stack frame. So it's always, so this is set to 120 because the base of the stack frame is 120. That's why, this means that the place that x is at, negative 16, is going to be 104 because 120 minus 16 is 104.
And you replace that with 14 or just for storing.
We're not touching RBP. We're changing the value at memory offset 104. So this is memory location. At that location, we're storing the value 14. Yeah. Okay, so let's go on to the next example. So now, what if one of the operands is not a variable, but an integer constant instead? So in this case, we have x equals 7, or sorry, x equals 7 plus b. The assembly code's pretty similar to the previous example. Now, instead of moving a value in memory to the REX register, we move the immediate value 7 into the A register. And then B is loaded in just as before, and then the addition is going to be the same as well, and the result is going to be stored in X just like before as well. So maybe you're starting to see the template that we're going to follow. So for some of these operands like add and subtract, you can actually pass an immediate value directly to the mnemonic, to the instruction. So you might be wondering, why don't we save instructions and make our compiler a little bit faster, our compile code faster, by just passing 7 directly to the add instruction here? Well, the reason why is because it's easier for us as a compiler writer to just follow a template where we move all the variables, all the values into these registers first, because then the rest of this code can be pretty much the same afterward. Let's just follow a template in implementing our compiler. So let's see this example. We'll walk through this one next. So x equals 7 plus b. Actually, I'll change this a to a hyphen. We don't know what's in it. Same as before, we assume that the base pointer is 120. That's the base of this stack frame. We're going to start with our first instruction here, moving the immediate value 7 into the A register. So we're going to change RAX to 7. Then we'll execute this line of code. So negative 32 RBX. What variable is this referring to? B, right? So negative 32 is here. That means we're going to be referring to the B variable. So we're going to move the value 5 into RBX. So RBX is going to be equal to 5. Next, we're going to move on to this add instruction. So what should be the result, and where should it be stored? Okay, 12. And what register is it stored in? RAX. So RAX will be equal to 12. And now finally, we're going to move the value in A register into negative 16 RPP. What variable does negative 16 offset refer to?
X.
X, exactly. So we're going to move this to 12. Okay, any questions? All right, hopefully we're going pretty slow and steady through this. I want to make sure this is very clear. And here's that template that I was talking about, kind of spelled out very clearly for you, hopefully, in this slide. And remember, all the slides are based off the same files that the course notes are based on. So if you want to go to the course website and check out the notes page for this presentation, it'll be the same content as are in the slides. You can find this template there. It'll be pretty helpful, I think, for implementing your compiler project. So the big idea, kind of small here so you can't quite see it, but the big idea, if I can zoom in, there we go, is that we have a move instruction, the first operand going into RAX, another move instruction, second operand going into RBX. Whatever the operator is, we emit that operator, RBX plus RAX, and then we move the value in RAX into whatever offset the destination variable is at. Okay. Now, I think this might be a good point to take a break, because division is going to be not similar, unfortunately, to everything else we've seen. So we'll go over that shortly. For now, I think we should just take a break. So I'm going to pause the recording. Okay. All right. So we'll continue from here. So now we'll talk about division. Now, division is going to be different from addition and subtraction and multiplication. I don't know exactly why, but probably has to do with the actual architecture of the chip, x86, 64 chips. But the big idea is that we can only use specific registers for division, and we have to use a special command in order to set up those registers. So for instance, if we want to perform 9 divided by 5, what we first need to do is move the value 9 to the RX register. So this is pretty similar to what we saw before, moving the first operand into a register, the A register. Then we move operand B, the second operand I should say, into the B register. So pretty similar to what we saw before so far. But then the weird thing that we have to do is called the CQO instruction. Now what this will do is combine the RDX and RAX registers into one pseudo register, you could say, which holds the sign extended numerator 9. Now the reason we have to do this is because the specification for the x86-64 assembly instruction set says that the numerator for division has to be 128 bits in size. But a normal register can only store at most 64 bits. So we have to call this CQO instruction to combine those two registers to form a 128-bit register suitable for division as the numerator. And then if we call the division instruction IDIV, integer division specifically, we only have to pass one operand because the RDX RAX register is implicitly going to be the numerator. And this will divide whatever is in this sign extended pseudo register by the one operand we give to IDIV, in this case RBX. Afterwards, the result is not going to be stored in RBX, the result is going to be stored in RAX. The quotient is going to be stored in RAX, and the remainder is stored in RDX. So it is kind of similar to addition and subtraction in that the first operand, one of the operands, actually does store the result. It's just split up over these two different registers. Okay, any questions? All right, I have a question for all of you now. Why do you think it's called CQO?
Sorting quotient of it.
Good guess, but no. Not quotient. Q does not stand for quotient. Give you another hint. A word refers to the size of a unit of data handled by an instruction set or a CPU. Traditionally, a word was 16 bits on x86-64. What?
Query?
Not query. So 16 bits. We have 64 bits in quarter, close, quad. So Q is quad, yes. Q is quad. We're converting from 64 bits to 128 bits. What do we think O stands for? No? What sea animal has 8 arms? Octopus, octo. So convert quad to octo. And if you look, actually, what's funny, I'll always make sure to point this out because I want to make sure nothing's arcane or too well hidden. I want to make sure it's all really clear. If we go back to the instructions here, this manual I showed earlier, there's actually other mnemonics for smaller variable sizes, because there are smaller registers you have access to as well. We won't be using them in this course, but there's other ones. There's CWD, convert word to double, CDQ, convert double to quad, and then CQO, convert quad to octo. In previous semesters of this course, I actually erroneously thought, Dr. Zillow and I both erroneously thought that we were supposed to use CDQ, but actually if you read here, CQO is the correct instruction to use. So if you look at the previous recordings for this course, if you decide to do that, you'll see that I use CDQ by mistake. The correct one to use is CQO. It shouldn't affect our compiler because we're not going to be testing integers large enough for it to matter. But just know that CQO is the correct one to use for 64-bit integers. Yeah.
So do you think CQO will always set like RAX as the numerator and RDX as like
It will always set RAX as the numerator, but the denominator is going to be specified as the single argument to IDIV. So in this case, RBX is the denominator because we're passing RBX to the IDIV instruction. Yeah. Oh, sorry. You have more question? More?
So RDX will always be the remainder?
Yes. RDX will always be the remainder. RAX will always be the quotient. Yeah. You have a question?
So you use IDIV, always whatever's on
Yes, yes. The RAX, really it's RDX combined with RAX, but effectively it's just RAX. Yeah.
I'm still confused as to why you need more space for the numerator.
It's just a specification. The instruction set tells us we have to do that.
Oh.
The specification tells us, yeah. So I mean, there's probably a reason for it. It probably was better for the chip designers, or it makes the code faster somehow. It makes your machine run faster by having RAX, by having these instructions set up in this way. All right, so we're all clear. You really don't have to know what this means. Practically for you, all you need to know is that you have to follow a different template when performing division. All right, so I think my next example is actually about division. Yeah, so let's continue with these slides. Yeah, so we use IDIV both for division and modulo because the remainder is always going to be stored in the RDX register afterward. We can use IDIV for both. Set up the predefined registers first, so RAX and RDX, and RBX for the operand, for the denominator. And then we retrieve the results from RAX and RDX. Now for the example, we have this function here, like we saw before. A is assigned to 9, B is assigned to 5, X is assigned to A divided by B. And so in this example here, we're going to walk through the steps to actually perform this single arithmetic operation, X equals A divided by B. So I'll turn this to red, and we'll get started. So the first thing we do is move negative 24 RBP into RAX. What variable does negative 24 RBP refer to? A. So we're going to negative 24 offset. That's going to be the value A. So we're going to put 9 into RAX. Now we'll go on to the next instruction. So negative 32 RBP into RBX. What's at negative 32 RBP? B. So negative 32 RBP is here. The stack goes down, so that's referring to the B variable. So we're going to grab 5 and put it in RBX. Now we perform the CQO instruction. So we're going to combine RAX with RDX. Really, the combination doesn't really matter, but what's in RDX doesn't really matter here. What matters is that we're combining them to form this sort of pseudo register, which is just going to be 9 for us, effectively. Yeah.
Is it always the two registers? What if you have three, for example, like 3 registers, 3 operations, and then you run CQO? What would happen?
3 registers and 3 operations. CQO only ever combines A and D, the A and D registers. It doesn't combine anything else. So it doesn't matter what you have before it. We could have swapped the order of these two operations, for instance, and this would still be the same. RDX and RDX would still be combined to form 9. Yeah. Yeah.
So how does it know which values like in the numerator and denominator? Is it just like based on the syntax of the IDIV itself?
IDIV, so IDIV always assumes RDX RAX is the numerator. So IDIV will always use this as the numerator. So we always, it's implicit that you know that RDX RAX is the numerator for IDIV. You just have to know that when you're writing this assembly code. And the as you can see here, I guess we'll go on to the next instruction now. The only argument we pass to IDIV is the denominator, which in this case is RBX, which we set up ourselves. So maybe what I should do here actually, just to make this even more clear, hopefully. Let's look at RDX separately. And now if we perform the IDIV instruction here, so we're dividing this 9 by RBX. So what's 9 divided by 5? 1 remainder 4. So 1 will go in the A register, and then 4 will go in the D register. And this doesn't really make sense anymore since they're no longer, the values aren't what they were before, so. Yeah,
What if it was instead 5 divided by 9, then it would just, the value would just all go into RDX?
so yes, RDX would just be 9, because 9 goes into 5 0 times, so it's 9 remainder. So it's just basic modulo, division to modulo. The only difference is, the only, I guess, twist is that we have to remember where we're storing all the results in using these assembly registers. So this is done. And finally, we're going to move RAX, which stores the quotient or the remainder. Which one? The quotient, right? The quotient is going to be moved into negative 16 RBP. What is that? X, right? So negative 16, that refers to X. Make this black, and we'll make this 1. Okay, so what if I wanted to change this to a mod B? What would I have to change in these assembly instructions over here?
You would want to access RDX instead.
Yes, I want to access RDX instead because that would store the remainder. So it's pretty simple to go between division and modulo. Yeah?
I actually had a question more specifically for the CodeGen project. So you're implementing the add, subtract, like all in the same method. So when you're returning division or modulo, you can always return RAX at the bottom. So at the bottom of your module one, could you move RDX into RAX?
Yeah, you could. You could. That's one idea.
Syntax should be RDX or RAX RDX. Move.
You could do that, yeah. So what your classmate is suggesting is, why don't we, instead of modifying this instruction here, why don't we just add another instruction? Make this a little bit smaller. Why don't we just add another instruction moving RDX into RAX? If all we're concerned about is the result of modulo. And you could do that. You could do that. And that's for homogeneity and your keeping the sameness in your template. It might make it easier for you in writing your compiler to do that. You can do that if you want to. Up to you. Yeah.
I'm so glad you understood that because I wasn't sure if I was clear.
No, I understand. I mean, I've written the whole compiler myself in plain C, so I understand the steps involved. Okay, yeah.
Do we only want to use CQO for like division, or could we also use it to like hold larger numbers for addition?
So that depends on, I'm not sure, and you'll have to read the specification. There might be instructions in the instruction set that enable you to add together 128-bit values. If you wanted to do that, it'll probably tell you what combined registers you'll have to look for, and you'll want to use CQO to set up those registers. Yeah, that's a good question. Okay, so I think what I'll do now is actually save these notes. Yeah, save this here, arithmetic, and we'll export this just as it is to, let's see, actually I'll leave it here for now. And I think that's it for the compiler. Yeah, so we've already seen all this, assembly code, modulo, how it all looks. Now, what I want to go over is the compiler project itself and how you can get started actually working on this thing. Has anyone tried to start it yet? Yeah. I know it was assigned in the previous lecture, a bit of a scheduling mishap on my part. We hadn't gone over assignments yet, so you weren't really fully equipped to actually tackle a project. So, but by the end of today, you should be able to start working on it. So let's go back to the course notes. So 2026. Actually, I have it open right here. Compiler project. Okay. This is the previous lecture that we saw. So the big idea is that, I think Ryan might have went over this, you're going to be defining these semantic actions for how you visit each node of the abstract syntax tree that is parsed from the simple IR input. So to visualize this, I don't think Ryan went over this in the previous lecture, but there's this link here, this handy link on the compiler project page to lab.antler.org. And what it lets you do is mess around with different grammars and visualize the abstract syntax trees that they produce. So here's an example of an abstract syntax tree. What you're going to be defining in the compiler project are a series of methods. So a method is a function associated with a class for visiting each one of these different nodes in this tree. So down here we have all these different nodes in this abstract syntax tree. Expression, and expression, stat, def, stat, etc. You're going to be defining methods that determine how to translate each one of these expressions into assembly code. That's what a compiler is. And this is not the only way to implement a compiler, but this is basically going to be the visitor patterns we're going to be using, where you define a way of visiting all the different nodes in a tree where the nodes might all be different kinds. So we have expression nodes here, statement nodes, definition nodes, a program node. You'll be defining methods for visiting all these different things and how to translate them into assembly. So that's visually what we're doing, turning this sort of tree structure into assembly code. This is how most compilers actually work. Okay. Now let me actually take a look at the code here. Should I knock back?
Are they compiling Morse code?
Yeah. Okay, CodeGen Project 1. Here we go. So for each part of the compiler project, you'll be tasked with implementing a different part of the compiler. So each part of the CodeGen project, you'll be implementing a different part of the compiler. The first parts you'll be implementing are going to be arithmetic and it's actually it, I think. No, arithmetic and branching. We'll go over branching in the next lecture, but you can actually get started on enter operation now, which is honestly, I think, the more difficult part of this assignment, the operations. Now, to begin working on this project, you'll want to follow these instructions. So you'll want to, clone this self-check repo, get your self-check set up so that way you can get feedback on your submission. Oh wait, sorry. That's not the first set of instructions here. Here they are. Where is it? Yeah. So you'll set up your git repo like we've been doing. Then you'll use this wget command to download the project starter code. So I've already done that, and you'll use this tar command here to unpack it. So I've done that here. You can see I have the starter code already in this directory. You'll start off with this cogen.template.cpp file. You'll want to move that into your cogen.cpp file. That'll be the one that your makefile looks for. So make sure to run this move command. That's important. I've already done that. So what you'll have is all these files here. The only one that really is important to you for this project is going to be cogen.cpp. All your work will be in that one file, cogen.cpp. So if we open this up, you can see it already has some code given to you. There's a variable here storing the byte width, the number of bits in a byte. Actually I should say the number of bytes within each of our variables, which we're going to be storing is just 8. The names of the registers that are general purpose registers we'll be using, I'm sorry, not general purpose, special registers we'll be using for passing parameters. That'll be useful later on in the course, in the assignment. Some other global variables here that you don't really need to worry about too much. A helper function for converting operands to their strings. So what this is useful for is if you pass in a token, so does anyone remember what a token is? We had seen it previously in the lecture on shells.
Unit of
Like a language,
input.
essentially, yeah, of input. So with these tokens, you can pass one to this helper function operand to string, and it will actually convert it to, if it's a variable, something like -16 RBP So if we were passing a variable whose offset was negative 16, it would print out, or it would return this string, negative 16 RBP. If we were passing a token that was an integer literal, it would return something like, e.g., 7, the value 7, if we passed the value 7, a token that was just the number 7 to it. So this is useful for handling different kinds of operands that might be variables or immediate values. So I recommend just using this helper function. Now in the project itself, here's all these methods I was talking about. As the course goes on, we'll be filling all these methods up with the definitions necessary to translate their corresponding constructs into assembly code. The main function simply just takes some input, runs the lexer, gets the token stream from it, runs the parser on that, and then actually walks the resulting parse tree to emit the correct assembly code. So for these functions, these methods, some of them are going to be given to you. So the first ones here, enter unit, enter local variables, and enter assign, they're going to be given to you. So if you click on this link, it will take you to the given definitions. Please just use these definitions. So enter unit, I'll copy this in. This is just going to emit the header content for your assembly code. So this .file section specifies the file name, .section, .note, .gnu stack, progbits. This is something you need just for your code to work without an error or a warning for with the GNU compiler. And then this .text section specifies that the rest of the file is going to be the actual code that's going to be executed in this assembly code. The rest of this assembly file contains the actual code to execute. Next we have enter local variables. This is a long one, so be glad you don't have to write this one yourself. This is actually probably the most complex part of the project, and we've done it for you. What this does is it actually sets up the symbol table. So we saw the symbol table earlier, that mapping of variables to their offsets from RBP. This function actually will set up all those offsets from the base pointer. So I'm not going to go over it in too much detail here, but I recommend reading this and trying to understand what's going on for yourself. There also are some other things that need to be done that I haven't gone over yet in this lecture that we'll learn more about when we get to the function calls lecture that this function sets up for you. So you can try reading it. It might be a little bit ahead of what we've gone over so far, but yeah. The main idea is that this sets up the function table, the symbol table for you. And then finally, enter assign. This one is a good one to use as a reference for implementing your own functions, because enter assign is probably the least complex of the three given to you, the three methods given to you. And this actually shows you how you're going to be implementing your own methods. So for instance here, in the assign statement, this is going to be a simple assignment. So A equals B, C equals 1, etc. The first thing we do is get the string for the operand. So if this was, for instance, if the operand was 7, this would go to $7. If it was A, it would be negative 24 RBP. That's what this operand would store. And you can get this from this context operand field. Now, when you're completing this project, the way to tell what fields are on each of these different parameters is to open the simpleir.g4 file. This is the grammar file that Antler uses to parse your input. So here we're dealing with an assign context, so we have to look for the assign grammar construct right here. So we can see that the assign has a variable, which is a name, and then an operand, which is a name or a number. So you can access the operand field, the operand part of this grammar rule, with the operand field of the context parameter. Likewise, to get the destination, let's see where it is. The destination is called variable, right here. You can get the variable field with this variable field as well on the context parameter. when you start writing this yourself, you'll get a feel for it and how to work with Antler. This is just sort of working with the Antler API. Each of these tokens has a getText method associated with it that accepts no arguments, and that will get you the raw text behind that token. So for instance here, we want to get the offset from RBP at which the destination variable lies. So we're passing to the symbol table. The symbol table is a mapping from strings to integers, so a mapping from the name of each variable to its offset. It's going to be negative in the case of local variables. We're passing in this case, the name of that variable as the destination of this assignment as the index of the symbol table, and then that's going to be printed out here along with the RBP. So if you haven't used C++ before, cout is the way you print things. So cout and then less than prints things to the console in C++. It's kind of weird. N means new line. You could also use \n. One more thing I'll mention, one very subtle gotcha with C++ is that the bracket notation for maps like this, if C++ looks in this mapping, symtab, string to integer mapping, and finds that the string you have passed it is not in that table, it will not throw an error. It will create a new entry in that table with the value 0 and return that. So that can be a big gotcha, a big like foot gun if you're not careful. If you want to avoid that, you can replace this with the .at method, and that will throw an error, throw an exception, if the string you pass to the table, to index the table, is not a valid key in that table. I mention it because several students have come up to me before with this problem. Also be aware of, well, that's it for now. Just worry about that. There's a lot of other subtle things in C++ that I can go on and on about, but this is probably the most notable thing right now is just you might want to use the .at method when accessing the symbol table instead of brackets. Up to you. I also recommend emitting comments for every one of your methods that you emit. So here we have this hashtag that's the beginning of a comment in assembly code, hashtag assign, and then we're assigning context operator getText to context variable getText. So we're just printing out in English what this instruction should be doing. That'll really help you debug your code if you emit these comments. And honestly, you could emit a comment at the end of each line. So we could say here, move operand into RAX, and that'd be another comment for us to identify what's going on. I recommend adding a lot of comments to your output because compilers are very tricky things to implement. All right, any questions so far? All right, so for you, you're going to be looking at operation. So if we look at operation, you'll see we have all these fields: variable, operand 1, operator kind, and then operand 2. We give you a lot of instructions in the assignment description on how to use these fields, but these are going to be the 3 fields you have access to from the operation context, which is going to be right here. So keep that in mind when you're implementing your compiler, this stuff. Okay, now for an important part, how the heck do we actually test this thing? So testing a compiler is often kind of tricky because a compiler, for it to actually produce any output, it kind of needs to all work at once. Like a lot of it needs to all work at once in order for it actually to compile, for compiled code to actually work. So to get around this, what we've done is we're giving you these hard-coded functions. These are not going to be ones that are given to you. These given to you ones are ones you can use for the entire course. You don't have to change them at all. These hard-coded ones, you're only going to be using these hard-coded definitions for this assignment. In future assignments, you'll be implementing these functions on your own, but these hard-coded definitions work for only the test cases that we're going to be using for this one assignment. This is to prevent you from having to implement the whole compiler at once. Instead, you can focus on just these 4 methods here, and the rest will just work for the specific test cases we give you. So I'll copy these in now. Yeah, or any questions? Okay, thought I saw a hand raised. So what we'll do is copy in these hard-coded functions. So enter function is going to be the first one. This might take a little bit, so I copy all these in. Am I missing a function definition here? I might be. Whatever, I'll just paste this in and it should work. Enter end. So you don't have to worry about what these functions do right now. We'll learn more about them later in the functions lecture. Yeah. Enter call. I'm wondering why I didn't have the function definition already there. Okay, that should be it. And then enter parameters. It just is empty for this assignment, so I'm not going to bother copying it in. Yeah, okay.
Pretty sure the enter function was there for the code that we download. I was just working on it this morning.
Okay, so I don't know why it's not here for me. Maybe I deleted it by accident or something, but all right. Let me try and make this, make sure it works. Enter local variables. Oh, I think I know what I did. I probably deleted enter function by accident when typing in enter local variable, so I'll delete this one. And there we go. So now it's compiling. So it's compiled. It seems to work. Now what we can do to actually test your code, we're going to give you 2 more files. This is going to be kind of cool, kind of weird too. So the first one is going to be this template.ir file. I'll just copy and paste this right here. So read the instructions, read the comments. Do not change any of the lines that say do not change in this file. These are going to be lines that just are boilerplate for you for testing your code. You can add more code here to test out different features of your compiler. So if you wanted to test out the ability to do an assignment, you could write that here, x equal a equals 1. Or we'll say maybe retval equals 1. Or not retval, result. So the cool thing about this code here is that it makes a call to this print int function, and will print whatever result you have stored in here. That print int function is actually not defined in simple IR. It's going to be defined in a C file that is called iolib.c. This is where printint and readint are defined. You can see we're using standardint.h to get the integer types. And then we're using int64t because all the values in our simple IR are 64-bit integers. And now what you can do, what this means you can do, is actually compile and link your simple IR code with this C code, as long as you follow the ABI correctly. So that lets us actually access and call this print int function here that's defined within our C code, which I think is pretty cool. We get to have this language interoperability. Now to actually test this, we'll follow these 3 steps. We'll run our CodeGen compiler on template.ir to produce this template.s file. Then we'll compile this and produce the template, or run the template. So let's try running this first. No errors. Let's see what's in template.s. We can see our compiler seems to work. We got some code emitted. Where's that instruction? Right here. Assign 1 to result. So this is the assign operation. It seems like it's working. And then we'll run GCC. Oops. Copy that again. We're going to compile the template.s file that we've produced with the iolib.c file and produce the template binary. And now if we run this, we can see the value 1 is printed. And that's actually what was in our If I can open this back up again. Template.ir file will be assigned 1 here. We can change this to 42. Run this again. And now it prints 42. So this is how you can kind of quickly test that your compiler is working. What I recommend doing is maybe adding another command to the end of the makefile here. Make sure to add it to the end of the makefile, not the beginning. Make it depend on the program, so it always compiles our code if it's not already compiled. And now we can just make test, and it'll actually run and test our code for us. So you can actually produce multiple template files if you wanted to. Just copy and paste those templates, create a bunch of different templates here, and you can have the test command run them all. And you can make sure they all work. So, all right. So I hope that gives you an idea of how to get started. Do you have any questions on how to get started with the CodeGen project? Okay. So remember, we're using these hard-coded, the given to you functions are given to you. You don't have to change them at all. For the whole semester, they're going to be fine to leave as is. The hard-coded functions, you're using them for this assignment only. In the next assignment, you'll want to start really from scratch and implement any functions we ask you to implement, which might include some of these hard-coded functions.
So in like CodeGen 2, we're not going to be using everything from CodeGen 1?
No, so we're making sure that your compiler, each part of the CodeGen project only targets a specific feature of your compiler. This is to make it easier for you to implement it and easier for, make it more fair for you to implement it, honestly. We shouldn't be testing you to implement the whole thing at once, so, yeah. So I hope you enjoyed this project. It's pretty fun. There's a saying that when you leave a programmer alone long enough, they make video games and compilers. Maybe you'll start to see why compilers are so much fun to build. When I took this course, we had to start from the tokenization. We wrote the whole thing in C. We had to start with writing the tokenizer, the scanner. We also had to write the parser. Then we had to write the actual compiler that translated the parse tree into the assembly code. So this is kind of starting you off with the back end of the compiler, just working on doing the assembly translation. So I hope you find it fun. I'm going to try and let you out of here before the thunder hits. So yeah, have a good time. I'll see you on Wednesday. If you have any questions, you can please ask me.